The morning of October 17th, 1944. Above Rabaul, New Britain, Lieutenant Robert Hanson pushed his F4U Corsair into a vertical dive from 22,000 feet, the altimeter unwinding as the bent-wing fighter accelerated downward. Below, a formation of Japanese bombers crawled toward American positions, their Zero escorts weaving protectively above them. Hanson's airspeed indicator swept past 400 miles per hour, 420, 440. The control stick grew heavier in his hands as air pressure built against the control surfaces, but the Corsair held together. 460 miles per hour, 480, 500. The stick shuddered slightly, but Hanson had learned through bitter experience that this aircraft, unlike anything the Japanese flew, could sustain speeds that would tear enemy fighters apart in midair. At 510 miles per hour, he pressed the trigger. 6 Browning machine guns hammered out 1,200 rounds in 3 seconds. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Tracer rounds converging on a Betty bomber that never saw the attack coming. Then Hanson hauled back on the stick with both hands, pulling 7 Gs as the Corsair's wings groaned but held, the aircraft clawing back toward altitude, while the Betty spiraled earthward trailing smoke. The entire engagement lasted 11 seconds. What Hanson knew, and what Japanese pilots defending Rabaul that morning could not have anticipated, was that American engineers at Chance Vought had built an aircraft capable of diving faster than any fighter in the Pacific theater, while retaining the structural integrity to pull out of those dives without disintegrating. This wasn't theoretical performance discussed in engineering reports. This was a weapon that redefined the physics of air combat, and Japanese tactics, refined over China and perfected at Pearl Harbor, offered no defense against it. The story of the Corsair's diving capability begins not with dramatic combat victories, but with methodical testing that revealed structural characteristics unprecedented in carrier-based fighters. In May 1940, when the F4U prototype first flew at Stratford, Connecticut, test pilot Boone Guyton recognized immediately that Chance Vought had created something extraordinary. The aircraft broke 400 miles per hour in level flight during its 7th test flight, becoming the first single-engine American fighter to exceed that threshold. But speed in level flight revealed only part of the aircraft's capability. During full-power dive tests conducted at Naval Air Station Patuxent River in Maryland throughout the summer of 1940, pilots pushed the prototype to speeds approaching 550 miles per hour in vertical dives from 45,000 feet. At those velocities, fabric-covered control surfaces began deforming under air pressure. Access panels rattled loose. In one test, engine failure occurred when oil pressure spiked beyond design limits. The tests clearly demonstrated that modifications would be necessary before production could begin. But the tests also revealed something that would fundamentally alter Pacific air combat. The Corsair's airframe, despite sustaining some damage to secondary components, did not break apart. The wings did not separate from the fuselage. The tail structure remained intact. Engineers examining the prototype after these punishing dives found stress fractures in expected locations, deformation of lightweight components, but no catastrophic structural failures of primary load-bearing elements. This was not accidental. The Corsair's distinctive inverted gull wing, designed primarily to shorten landing gear struts while maintaining propeller ground clearance, created additional structural benefits that engineers had not initially anticipated. The wing's center section formed an integral part of the fuselage structure, a single metal unit rather than separate wing and body sections joined together. This construction method, borrowed from racing aircraft design, distributed aerodynamic loads across a larger structural area. The wing itself incorporated heavy-gauge aluminum alloy spars running the entire span, with multiple ribs spaced closely together to prevent skin buckling under compressive loads. Where most fighters of the era used fabric covering over portions of control surfaces to reduce weight, Vought engineers specified metal skin throughout, even though this added several hundred pounds to empty weight. The rationale was straightforward. Fabric deforms at high speeds, creating drag and reducing control effectiveness. Metal skin maintains its shape regardless of velocity. Production F4U Corsairs that began reaching Marine squadrons in February 1943 incorporated lessons from those prototype dive tests. Fabric-covered control surfaces were eliminated entirely, replaced with aluminum panels reinforced with internal ribbing. Access panels received improved latching mechanisms. The engine mounting structure was strengthened to handle increased vibration during high-speed flight. These modifications added approximately 800 pounds to the aircraft's empty weight compared to the prototype, but they created a fighter that could routinely sustain dive speeds exceeding 470 miles per hour without structural damage. The practical implications of this capability became apparent during the first combat deployments to the Solomon Islands. Marine pilots, many of whom had flown F4F Wildcats and understood intimately the limitations of that earlier fighter, found themselves flying an aircraft with fundamentally different tactical options. A Wildcat in a vertical dive reached terminal velocity around 340 miles per hour, at which point increasing drag balanced engine power and gravity. The Corsair, with its cleaner aerodynamics and more powerful engine, could exceed 480 miles per hour in a dive while still accelerating. This meant that a Corsair pilot with an altitude advantage could dive on Japanese formations at speeds no enemy fighter could match or even approximate. Japanese pilots flying the Mitsubishi A6M0, the most common opponent in the Pacific, discovered this disparity through costly experience. The Zero's lightweight construction, which gave it legendary turning ability and climb performance, became a liability at high speeds. After American forces captured an intact Zero on Akutan Island in June 1942 and conducted extensive flight testing at Naval Air Station San Diego, pilots reported that the aircraft's control surfaces stiffened dramatically above 350 miles per hour. This wasn't a design flaw so much as a deliberate safety feature. Zero engineers understood that the aircraft's lightweight wing structure could not withstand high-speed maneuvering loads, so they designed the control system to become increasingly difficult to move as airspeed increased, preventing pilots from applying control inputs that might break the aircraft. At speeds above 400 miles per hour, speeds routinely achieved by diving Corsairs, the Zero became effectively uncontrollable. Pilots attempting to follow Corsairs into vertical dives found their control sticks locked solid, unable to track the diving American fighter or pull out of the dive themselves without reducing speed. Multiple combat action reports from Marine squadrons operating over the Solomons during 1943 and 1944 document Japanese fighters entering vertical dives in pursuit of Corsairs, then breaking apart in midair as pilots attempted high-G pullouts at speeds exceeding their aircraft's structural limits. Major Gregory Pappy Boyington, commanding VMF 214, the famous Black Sheep Squadron, explicitly instructed his pilots to use vertical maneuvers against Zeros. His tactical guidance, recorded in the squadron operations log from September 1943, emphasized that the Corsair's diving advantage was absolute. If a Zero attempted to follow you into a dive exceeding 400 miles per hour, Boyington wrote, maintain your dive. The enemy cannot follow without losing control or breaking apart. Use your speed to extend away, then climb back to altitude advantage before re-engaging. This tactical approach, which Marine pilots called boom and zoom, represented a fundamental departure from the turning dogfights that characterized early Pacific air combat. When F4F Wildcats faced Zeros in 1942, American pilots had to turn with their opponents because the performance gap didn't allow alternative tactics. The Wildcat was slower, climbed worse, and couldn't dive away effectively. Pilots survived through defensive maneuvers like the thah weave, mutual support tactics that prevented Zeros from establishing firing positions. The Corsair changed everything. Marine pilots no longer needed to turn with Zeros. They climbed above enemy formations, dove through them at speeds exceeding 500 miles per hour, fired during the brief moment their trajectories intersected, then climbed back to altitude, using the enormous kinetic energy accumulated during the dive. The entire attack sequence occurred so quickly that Japanese pilots often didn't realize they were under attack until tracers passed through their formation. Training pilots to exploit the Corsair's diving capability required overcoming deeply ingrained instincts about fighter combat. At Naval Air Station Melbourne in Florida, where Marine pilots completed advanced fighter training before deploying to the Pacific, instructors spent considerable time teaching students to resist the temptation to turn with enemy fighters. Second Lieutenant James Sweat, who would later become an ace flying Corsairs, described his initial reaction to this training as counterintuitive. Everything about fighter pilot culture emphasized aggressiveness, closing with the enemy, staying in the fight. The boom and zoom doctrine demanded patience, discipline, and willingness to break off engagements, even when the enemy was visible and vulnerable. Instructors used a training technique borrowed from the Flying Tigers in China. They paired students flying Corsairs against instructors flying captured Japanese aircraft or American fighters configured to replicate zero performance characteristics. Students were instructed to climb to altitude, dive through the enemy formation at maximum speed, and climb back to altitude without attempting to turn with their opponents. The first few times students attempted this maneuver, most instinctively pulled back on the stick too early, bleeding off speed in a climbing turn that left them vulnerable to counterattack. The instructors would then demonstrate the correct technique. They would dive past the student, accelerate to over 400 miles per hour, then pull up in a zoom climb so steep it appeared nearly vertical. The Corsair would trade its accumulated kinetic energy for potential energy, rocketing back to altitude faster than the pursuing aircraft could climb. Students watched from behind as the diving Corsair disappeared below them, then reappeared thousands of feet above them 30 seconds later. The demonstration was visceral proof that the doctrine worked, that patience and energy management defeated aggressive turning. Lieutenant Commander Thomas Blackburn, who commanded VF-17, the first Navy Corsair squadron to see combat, emphasized in his training syllabus that the aircraft's structural strength was not infinite. While the Corsair could sustain dive speeds exceeding 500 miles per hour, pilots needed to monitor their airspeed carefully and begin their pullout with sufficient altitude to complete the maneuver safely. Blackburn calculated that at 500 miles per hour, a 7G pullout required approximately 4,000 feet of altitude. Pilots who delayed their pullout until they had less than 4,000 feet remaining risked impacting the water or ground before completing the recovery. This calculation became ingrained in Corsair pilot training. Instructors taught students to maintain altitude awareness during every dive, checking their altimeter continuously rather than focusing exclusively on the target. The rule was simple. If you dive below 8,000 feet and haven't fired yet, abort the attack and climb back to altitude. The enemy bomber or fighter you didn't shoot down was better than dying by flying into the ocean because you pulled out too late. This discipline saved lives. Combat reports from 1944 include multiple instances of pilots aborting attacks because altitude became insufficient, climbing back to altitude, then successfully completing the attack on a second pass with proper altitude management. The maintenance crews who kept Corsairs flying in forward combat areas understood that the aircraft's structural integrity depended on proper inspection and repair procedures. Staff Sergeant Michael Junk, who served with VMF 121 at Guadalcanal, described the post-flight inspection routine his crew followed after every mission. They examined wing spar attachment points for cracks or deformation. They checked control surface hinges for excessive wear. They inspected the fuselage skin around engine mounting points for wrinkles or buckling that might indicate structural stress beyond design limits. When his crew found issues, they documented them in detailed maintenance logs that tracked each aircraft's structural condition over its service life. Corsairs that repeatedly flew high-speed dive missions accumulated more stress than aircraft used primarily for bomber escort or ground attack. Junk's records show that some aircraft required wing spar replacement after fewer than 300 flight hours, while others flew over 500 hours, before showing similar wear. The difference correlated directly with mission profiles. Aircraft flown by aggressive pilots who routinely dove at maximum speed and pulled high-G recoveries wore out faster than aircraft flown more conservatively. This created a resource management challenge for squadron commanders. The most aggressive pilots, the ones who routinely achieved kills and returned unscathed, were also the ones whose aircraft required the most maintenance. Squadron commanders had to balance the desire to keep their best pilots flying against the reality that their aircraft needed more frequent inspections and repairs. Some commanders assigned their ace pilots to the newest aircraft in the squadron inventory, ensuring they had fighters with maximum structural integrity for their demanding mission profiles. Other commanders rotated aircraft assignments to distribute wear more evenly across the fleet. The Japanese response to Corsair diving tactics evolved as the war progressed, but remained constrained by fundamental limitations. In March 1944, Japanese Naval Air Force headquarters in Tokyo distributed tactical guidance to fighter units throughout the Pacific. The document, captured after the war and translated by American intelligence officers, acknowledged that American fighters possessed superior diving performance. Japanese pilots were instructed to maintain altitude advantage whenever possible, to avoid pursuing diving American fighters, and to rely on tight formation discipline to provide mutual defensive fire against diving attacks. But maintaining altitude advantage required climbing above American formations, which itself required time and fuel. By mid-1944, Japanese air groups were increasingly fuel-constrained. Tankers carrying aviation gasoline to forward bases were being sunk by American submarines faster than they could be replaced. Many Japanese fighters flew combat missions with reduced fuel loads, limiting their ability to climb to high altitude and remain there long enough to gain positional advantage over American formations. The guidance also assumed that Japanese pilots would see diving Corsairs early enough to take evasive action. In practice, this rarely occurred. Corsairs diving from 25,000 feet toward targets at 15,000 feet covered that vertical distance in approximately 25 seconds. The human eye struggles to detect aircraft diving directly toward the observer, as the target's apparent size changes slowly until the final seconds before attack. Japanese pilots positioned lower in the formation often didn't see diving Corsairs until tracers started passing through their aircraft. First Lieutenant Donald Aldrich, flying with VMF 215 over the Philippines in October 1944, described intercepting a formation of Japanese bombers escorted by 8 Zero fighters. The Corsairs held altitude advantage, positioned at 28,000 feet, while the Japanese formation flew at 18,000 feet. Aldrich led a 4-plane division in a diving attack, reaching 520 miles per hour before firing on the lead bomber. His burst struck the bomber's wing root, and the entire wing separated from the fuselage, the bomber disintegrating before any crew members could bail out. Aldrich's wingman targeted a second bomber in the same diving pass, scoring hits on the fuselage that ignited fuel tanks. The 3rd and 4th Corsairs in the division each fired on Zero fighters, attempting to position themselves to defend the bombers. Both Zeros were hit, one going down immediately, the other spiraling away, trailing smoke. The entire attack sequence, from the moment the first Corsair began its dive to the moment the last Corsair pulled out and climbed back to altitude, lasted 38 seconds according to gun camera timing marks. The remaining Japanese bombers scattered, abandoning their formation and attempting to flee individually. The Zero escorts, rather than pursuing the climbing Corsairs, remained with the bombers, providing what defensive cover they could. Aldrich assessed this as rational behavior under the circumstances. Japanese pilots understood they couldn't catch the Corsairs in a climb, so attempting to pursue would only separate them from the bombers they were assigned to protect. By staying with the bombers, they at least provided defensive machine gun fire that might deter subsequent attacks. But the Corsairs were far from finished. After climbing back to 30,000 feet, they repositioned and dove again. This second attack destroyed 2 more bombers and damaged a third. The Japanese formation, now reduced to half its original strength and scattered across miles of sky, abandoned its mission and turned back toward base. The entire engagement cost the Japanese 6 bombers and at least 2 fighters confirmed destroyed. American losses: 0 aircraft, 0 pilots, minimal ammunition expenditure. This pattern of engagement became standard operating procedure for Corsair squadrons throughout 1944 and 1945. Climb high, dive fast, attack decisively, climb back to altitude, repeat. The tactics exploited the Corsairs' structural advantages so systematically that Japanese formations often disintegrated after the first diving attack, bombers and fighters scattering rather than maintaining formation discipline through subsequent attacks. This psychological effect multiplied the tactical advantage, A scattered formation was easier to destroy piecemeal than a tight formation providing mutual defensive fire. The structural engineering that enabled these tactics represented American industrial capability applied to a specific tactical problem, while Japanese aircraft designers prioritized maneuverability and range, often accepting reduced structural strength to minimize weight. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. American designers possessed both the industrial capacity, engineering knowledge to build heavier, stronger aircraft without sacrificing performance. The Pratt & Whitney R 2800 double wasp engine, producing over 2,000 horsepower, generated enough thrust to accelerate a 9,000-pound fighter to speeds that would have been impossible with lighter engines. The engine itself represented remarkable engineering. 18 cylinders arranged in 2 rows of 9, air-cooled, each cylinder displacing 155 cubic inches. Total displacement, 2,800 cubic inches, hence the R2800 designation. This massive engine, weighing over 2,000 pounds, generated power densities approaching 1 horsepower per pound of engine weight, a figure that contemporary Japanese engines could not match. The result was an aircraft that could sustain high-speed flight while carrying armor protection, self-sealing fuel tanks, and heavy armament, features that Japanese designers often omitted to reduce weight. Combat over Rabaul during the first 3 months of 1944 demonstrated the tactical implications of the Corsair's structural superiority. Marine Air Group 14, operating from Bougainville, flew daily fighter sweeps over Rabaul's airfields, where Japanese forces maintained substantial fighter strength. These missions typically involved 6 to 12 Corsairs, climbing to altitudes between 20,000 and 25,000 feet, then diving on Japanese formations, taking off or landing. On January 17, 1944, 8 Corsairs from VMF 321 intercepted 15 Zeros, attempting to engage American bombers near Lakunai airfield. The Corsairs held altitude advantage, positioned 3,000 feet above the Japanese fighters. Lieutenant Jefferson de Blanc led the attack, diving through the Zero formation at over 480 miles per hour. His burst destroyed 1 Zero, which exploded when 50 caliber rounds ignited its unprotected fuel tanks. De Blanc's wingman, Lieutenant Robert McClurg, fired on a second Zero during the same diving pass, sending it down trailing smoke. The remaining Zeros attempted to follow the diving Corsairs. Combat camera footage from de Blanc's aircraft, analyzed after the mission, shows several Zeros entering steep dives with their engine nacelles trailing white vapor, a characteristic sign that their float-type carburetors were cutting off fuel flow during negative G maneuvers. The Zero's carburetor design, which worked adequately during normal flight, could not maintain fuel flow during prolonged vertical dives. At least 2 Zeros visible in the gun camera footage appear to be flying with dead engines, powerless, as they attempt to follow the American fighters downward. The Corsairs completed their diving attack, pulled out at 8,000 feet, and climbed back to 23,000 feet in approximately 90 seconds. The Zeros that had followed them down were still climbing slowly back to altitude when the Corsairs made their second attack pass. This time, with even greater altitude advantage and Japanese pilots still disorganized from the first attack, the Marines shot down 4 more Zeros without taking any damage themselves. The engagement lasted 8 minutes. American losses, 0. Japanese losses, 7 confirmed destroyed, possibly more that went down over water or crashed attempting to return to base. This pattern repeated across dozens of engagements during the Rabaul campaign. Japanese pilots, many of them experienced veterans with hundreds of hours of combat time, found themselves unable to counter tactics that exploited simple physics. A fighter diving from altitude converts potential energy into kinetic energy. A heavier fighter with a more powerful engine accumulates more energy. A structurally stronger fighter can sustain higher speeds and pull out of steeper dives. The Corsair possessed all 3 advantages. Japanese tactical response evolved slowly, constrained by the Zero's fundamental design limitations. By February 1944, Japanese commanders at Rabaul instructed their pilots to avoid vertical engagements with Corsairs. If attacked from above, pilots were told to maintain altitude and turn toward the attacking aircraft, forcing them into a turning fight where the Zero's maneuverability advantage might compensate for its speed deficit. But this tactical guidance assumed Japanese pilots would see the attack coming and have time to maneuver. At 500 miles per hour, a diving Corsair closed a 5,000-foot separation in less than 7 seconds, often insufficient time for even an alert pilot to react. Some Japanese pilots attempted to match Corsair dive speeds by pushing their aircraft beyond designed limits. The results were predictable and tragic. Multiple American pilots reported witnessing Zeros breaking apart in midair, wings separating from fuselages, as the lightweight structure failed under aerodynamic loads it was never designed to handle. Lieutenant Philip DeLong, flying with VMF 122, observed a Zero attempting to follow his wingman into a dive during an engagement over Duke of York Island on February 23, 1944. The Zero's left wing folded upward at approximately 400 miles per hour, the entire wing separating from the fuselage in a spray of rivets and aluminum fragments. The fuselage tumbled earthward, with the pilot still inside, no possibility of bailout. The psychological impact of this structural disparity compounded its tactical effects. Japanese pilots began to recognize that diving attacks by Corsairs represented essentially unavoidable death. There was no defense. You couldn't outturn the attack because it happened vertically. You couldn't outclimb the attacker because they already held altitude advantage. You couldn't escape by diving because the Corsair was faster. The only option was to see the attack early enough to take evasive action before the Corsair reached firing range, but that required constant vigilance while maintaining formation discipline, escorting bombers, and watching for other threats. Combat stress studies conducted after the war by military psychologists found that situations offering no defensive options produced significantly higher rates of combat fatigue than situations where pilots felt they could influence outcomes through their actions. Japanese pilots facing Corsairs in late 1944 described feelings of helplessness, knowing that survival depended largely on whether American pilots chose to attack their particular formation on any given day. This psychological burden, combined with increasing fuel shortages, declining pilot training quality, and numerical inferiority, created conditions where Japanese fighter effectiveness declined even when aircraft were available. The Corsair's diving capability produced measurable effects on combat outcomes. Navy and Marine Corps fighter squadrons equipped with F4Us achieved kill ratios, averaging 11-to-1 across the entire Pacific campaign. This figure includes all combat from February 1943 through August 1945, encompassing encounters against both experienced Japanese pilots early in the war and poorly trained replacements in 1945. The ratio cannot be attributed solely to the Corsair's structural strength, as many factors influenced combat outcomes, but tactical reports consistently identify vertical attacks as the primary method by which Corsair pilots achieved victories. Marine ace First Lieutenant Robert Hanson, who opened this narrative, shot down 25 Japanese aircraft in 17 combat missions between November 1943 and February 1944. His combat reports describe vertical diving attacks in 23 of those 25 engagements. In only 2 instances did Hanson engage in turning fights, both times when altitude advantage was unavailable and he needed to defend bombers under attack. His preferred tactic, recorded in debriefing transcripts, emphasized diving through enemy formations at maximum speed, firing only when the target filled his gun sight, then climbing back to altitude regardless of whether the burst scored hits. This approach, which Hanson called single-pass attacks, maximized the Corsair's strengths while minimizing exposure to enemy fire. A Corsair diving at 500 miles per hour presented an extremely difficult target. Japanese pilots attempting to fire at the diving fighter had to lead the target by substantial amounts to account for the closure rate, a calculation that became nearly impossible during the chaos of combat. Defensive fire from bomber formations proved equally ineffective, as the closure rate gave gunners less than 2 seconds to acquire the target, track it, and fire before the Corsair flashed past. The structural testing that enabled these tactics continued throughout the war, as engineers refined the Corsair design. The F F4U variant, which entered service in October 1944, incorporated a more powerful R280018W engine, producing 2,300 horsepower with water injection. This increased power allowed even higher dive speeds. Test pilots at Patuxent River routinely exceeded 530 miles per hour in vertical dives during acceptance testing, and the strengthened airframe sustained these speeds without permanent deformation. Later variants included additional structural reinforcements based on combat damage analysis. Engineers studied Corsairs that returned from missions with battle damage, identifying which areas sustained hits and how the structure responded. This data informed changes to the F4U model, including thicker wing skins in areas frequently struck by ground fire, reinforced engine mounting structures, and improved fuel tank protection. These modifications added weight but improved survivability, without compromising the aircraft's fundamental diving capability. The Japanese Navy attempted to develop fighters capable of matching the Corsair's performance. The Kawanishi N-1K2 Shiden Kai, introduced in late 1944, incorporated heavier structural elements and automatic combat flaps designed to improve high-speed handling. The Mitsubishi A7M Repu, intended as the Zero's successor, featured a more powerful engine and strengthened airframe. But both aircraft entered production too late and in too few numbers to affect combat outcomes. By the time these improved fighters reached operational units, American air superiority was absolute, and Japanese pilot quality had declined to the point where equipment advantages could not compensate for training deficiencies. The few encounters between Corsairs and N-1K, two fighters that occurred during the Okinawa campaign in April 1945, demonstrated that even Japan's most advanced fighters could not match the Corsair's vertical performance. Lieutenant Philip Torrey, flying with VMF 441, engaged 4N-1K2 fighters over IE Shima on April 10, 1945. His combat report describes diving from 19,000 feet at over 500 miles per hour, destroying 1N-1K2 on the first pass. When the remaining Japanese fighters attempted to follow his dive, Torrey maintained his speed and extended away, opening the range to over 2 miles before climbing back to altitude. The Japanese fighters, despite being newer designs with more powerful engines, could not close the distance during the dive or match his climb rate afterward. This engagement, typical of dozens that occurred during the final months of the war, demonstrated that the Corsair's diving advantage derived not from any single feature, but from the systematic application of American engineering and industrial capabilities. Powerful engines, strong structures, sophisticated manufacturing techniques, and rigorous testing combined to create an aircraft that simply performed better across the envelope than anything Japan could produce. The diving capability was merely the most dramatic manifestation of this superiority. The legacy of the Corsair's structural strength extended beyond World War II. During the Korean War, F4U and F4U variants flew ground attack missions against North Korean and Chinese forces from June 1950 through July 1953. These aircraft, many of them manufactured 5 or more years before the war began, regularly dive-bombed targets at speeds exceeding 450 miles per hour, while carrying external ordnance loads that would have grounded earlier fighters. The structural margins built into the design during World War II allowed the aircraft to perform demanding missions a decade after its introduction. Marine Corsair pilots in Korea reported that the aircraft's diving capability remained valuable even when attacking ground targets. Diving at high speed reduced exposure to anti-aircraft fire, as gunners had difficulty tracking the rapidly descending fighter. The ability to pull out of steep dives at high G loads allowed pilots to deliver ordnance accurately from near vertical approaches, then escape at low altitude before enemy gunners could react. These tactics, developed against Japanese fighters over the Pacific in 1944, proved equally effective against Chinese gun positions in 1952. The Corsair remained in production until December 1952, 12 years after the prototype's first flight. Over 12,500 aircraft were manufactured, one of the longest production runs of any American fighter. Many factors contributed to this longevity, but the fundamental soundness of the original design played a central role. An aircraft strong enough to sustain 500-mile-per-hour dives in 1940 remained strong enough to carry heavy ordnance loads in 1952. The 58 structural engineering decisions made by Vought designers in 1938 and 1939, informed by racing aircraft experience and validated through punishing flight testing, created a fighter that served effectively for more than a decade. The story of Japanese pilots, never knowing that Corsairs could dive at 500 miles per hour and pull out without braking, is ultimately a story about the consequences of industrial capacity and engineering philosophy meeting in combat. Japan designed fighters optimized for turning performance and range, accepting reduced structural strength as a necessary compromise to minimize weight. America designed fighters optimized for speed and durability, accepting increased weight because powerful engines and advanced manufacturing could compensate for it. Neither approach was inherently superior in abstract terms. In the specific context of the Pacific War, where American industrial production could field newer, heavier fighters in increasing numbers, while Japanese production struggled to replace losses, the American approach produced decisive advantages. The Corsairs' ability to dive faster than enemy fighters could follow, while retaining the structural integrity to pull out of those dives repeatedly over hundreds of combat missions, exemplified how systematic application of engineering knowledge and manufacturing capability translated into tactical superiority. For the Marine and Navy pilots who flew Corsairs over the Pacific, the aircraft's diving capability represented something more fundamental than tactical advantage. It represented a reversal of the fear and disadvantage that characterized early Pacific air combat when American fighters were outperformed by Japanese opponents. Flying a Corsair, a pilot knew that altitude advantage translated directly into combat superiority. If you held the high ground, you controlled the engagement. You decided when to attack, how to attack, and when to disengage. The enemy's only option was to evade or die. This psychological advantage, perhaps even more than the mechanical advantages that enabled it, changed the nature of Pacific air combat. American pilots stopped fighting defensively and began hunting aggressively. They stopped accepting even exchanges and demanded overwhelming superiority. They stopped treating Japanese aircraft as invincible and recognized them as fundamentally limited designs flown by increasingly inexperienced pilots. The Corsair's ability to dive at 500 miles per hour and survive made this transformation possible by providing an aircraft whose capabilities matched the aggressive tactics that American commanders wanted to employ. When Robert Hanson dove his Corsair through that Betty formation over Rabaul on October 17th, 1944, reaching 510 miles per hour, before pulling out with 7 Gs on the airframe, he was executing a maneuver that would have killed him in any Japanese fighter then flying. The Zero pilots escorting those bombers understood this disparity, even if they lacked the technical knowledge to explain it. They had watched their comrades die attempting to match American dive speeds. They had seen wings fold and fuselages break apart. They knew that when Corsairs held altitude advantage, survival became a matter of luck rather than skill. That knowledge, that understanding that the enemy possessed capabilities you could not counter, spread through Japanese fighter units during 1944 like a virus eroding combat effectiveness. It appeared in intelligence reports, in pilot diaries, in tactical guidance that warned against vertical combat. It contributed to declining morale, increasing reluctance to engage, higher rates of psychological casualties among pilots who flew mission after mission, knowing each sortie might be their last, and there was nothing they could do to improve their odds. The Corsair's structural strength, expressed through its diving capability, thus became more than a tactical advantage. It became a weapon of psychological warfare, a demonstration of American industrial and engineering superiority made visible in every engagement. Japanese pilots didn't need engineers to explain why Corsairs could dive faster and survive higher G-loads. They simply needed to watch their wingmen die trying to match those maneuvers to understand that the war was lost. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.